So this is example number 1 for buckling. Let's consider this problem. In this particular problem, what we have is we have one. You have to understand the problem that you have in hand first. You always need to read the problem carefully and highlight the most important things of the problem itself. So in this particular problem, let me change my colors here. What we have is the problem set has one end fixed and the other end pinned. Okay, those two are very important points, because then it's going to depend on the end fixity of your problem. So it's saying this end is fixed, one end is fixed, and one end is pinned. Now, pin, there are many ways you can put a pin. Okay, so this end is pinned. And you used to put a roller, but there are other ways to do that. I will talk about that in a moment. And we're going to have a compressive load. Okay. Note that the buckling is always a compressive event, not a tensile event. The problem also said that this is a low carbon steel. Is a rectangular cross section, gives you the height as 0.5 and the width as 1.5. Now, the problem is divided in two parts. The first part, we want to find the allowable buckling load. I'm going to explain that in a minute. What does that mean? And so basically, what we are looking for, what is your pre-critical for this particular problem, and what is your critical stress? Okay. For the second part of the problem, we are given, same for this particular case, the last case, go and given a concentric load of 10,000 pounds, and using a design factor 1.5, you want to determine if the column is going to withstand that load. And if it doesn't, give some recommendations. So in this part of the problem, what they're saying is a concentric load. So the load is right in the center, so it's P, and you have a design factor 1.1. In the problem, looking at the material properties, you can immediately find this is 43, 10 to the 3 psi. You can find that E is equal to 30 times 10 to the 6 psi. Okay, so let's start with the first part of the problem. We want to find the allowable buckling load. Before we move on, let's understand a few things here. When I'm talking about the allowable buckling load, why do I need that allowable? Why do I care for it? First of all, we're going to plot this, or what I call is RA actual, right? And then you got your sigma, and your actual buckling curves actually many times just look something like this. Okay, this is more or less your actual buckling load curve. Although using the J.B. Johnson, then your curve actually becomes like this, where this is the J.B. Johnson and this is Euler. And what we are trying to say here is, when you're working in this type of problems, you want to, for a particular RA of the problem, slenderness ratio, you're going to have a availability of the stress or the load, right? So this is the how much it is really available. This is the max you can possibly have. This is the amount available, sigma available. Okay. Now, if you, by any chance, at any given point, you have a point that requires this amount of a load level of stress, right? If it says this is what is required, you know that's not going to be possible at all. Why? Because I'm asking more than what my column can demand. Okay, so that's why anything below this, if you are exactly at this point right here, your factor of safety is going to equal to 1. You will be onset of failure. If your factor of safety is in this region, your factor of safety is going to be bigger than 1 because it's going to be safe. If anything beyond this point, anything above this, this is factor of safety will be less than 1, meaning that it has failed because it does not have that much capability in the structure to withstand that load. Okay, so this is very important. And the second thing that you have to keep in mind that regardless, sometimes we draw your columns horizontally or sometimes we draw your columns vertically. It's the same problem. Doesn't matter how you take it. The important thing is that the load has to be in compression. Buckling is subject to a compression phenomena, not a tensile phenomena. So if you had a case in which you had a column and you had a tensile load, you know that this is not a buckling problem. This is not buckling. Has nothing to do with buckling. Okay? So what we are trying to do in the first part of the problem is we want to identify for the given problem for each one of these lengths, what is the allowable buckling load? How much is the maximum this can possibly have? Okay, so second thing that we have to do in the problem to understand this problem, we come to this chart and now we need to understand from this chart which is the case that we are working with. We are saying that one of the ends was fixed, the other one was pinned. So let's work our way around this. The way this is given here, this actually is a pin. Okay, so this cannot be a boundary condition because this is pin. These all are fixed ends. So this is fixed, this is fixed, this is fixed. And you can see because of you have a zero slope, zero slope, zero slope. And then on this side, this is actually a fixed end. This is how we model fixed end. And so you know that this is fixed in this direction, as you can see, right? This is pin. So this possibly could be acceptable. This is how you model pin. This is identically same as taking a beam, putting a roller on the side, and putting a roller. These two problems are identical, okay? And then this is free, okay? And we don't want free, so that's not the problem. We are looking for fixed. We want a pin end on this end. This is free. And you can see that this is pin again. This is pin. So the case that we are working with is this particular case. So you know your C is equal to 2. Your effective length will be the total length divided by the square root of C, or L divided by square root of 2. We will do that for each one of the cases that we will work with. Okay. With that said, let's start. First thing we're going to do in the first part of the problem, this is part A of the problem. The first thing we will do is we will find your area, cross-sectional area. Okay, the cross-sectional area of this column looks something like this, where this is your base, this is your height. Height was 0.5, your base was 1.5. Okay, so in this problem, this is 1.5 times 0.5, and that gives you 0.75 inches squared. Your moment of inertia is BHQ over 12. You substitute the values, you find the value that you get is, this is the value of a moment of inertia to the fourth power. Then you can find your radius of gyration. Your radius of gyration is I over A is equal to 0.14434 inches. You need to find your slenderness critical ratio. Your book calls it L over K over 1. And this is equal to 2 times E pi squared over sigma yield. This is yield strength or tensile strength in many textbooks, compressive. Okay, so this is actually, and just to clarify this, this is compressive, not tensile. Okay, so if we replace the values, I have the value here. These two values are given here. So if I replace them here, then I will get a value of 117.37. Okay, the slenderness ratio. This is the value you get, and is dimensionless quantity. Okay, so let's move on in the problem now, and let's do the first part of the problem. And in this part A, the part A of the problem says the first length, you want to find the critical load for L is equal to 0.5 feet. You need to convert that into inches first because everything else is given in inches. So L effective will be L over square root of C, and that will give you 6 square root of 2, and that gives you 4.24 inches. Okay, and then you have, this is RA is equal to LE over your radius of gyration. That gives you 4.24, and the value K comes from here, this value right here. So we replace that here, 0.144, and that gives you 29.39. And you see immediately that this particular column is bound by RA and RC, and you can see this is equal to, RC was equal to 117.35. So basically what we are saying is, in this particular column, we are, this is somewhere here, this is your slenderness, critical slenderness ratio, and somewhere here, this is 10. So you can see that the equation that we should use, this is the intermediate column, so therefore the proper equation used is J.B. Johnson equation. Okay, so the J.B. Johnson equation then for this particular problem says that your P critical is multiplied by the area, gives you sigma yield in compression. I like to put the C there so it's clear that we are working in compression. Many times your E also has to be in compression. That is a distinction. But let's put RA 2 times pi squared. When I replace all the values, I have your RA here. So in this problem, I have the value of RA. That's what goes inside here. Your value of area was 0.75, and this comes from your material properties. So the value of your P critical for this particular column is 31,238 pounds. And you can see that anything that will be acceptable has to be, P has to be less or equal than P critical for this to be safe. And want to emphasize this again, this has to be in compression. Okay, it's not a tension phenomenon. Okay, so this is the first length. Let's move on to the second length of the problem. Okay. So the second length, we want to find the pre-critical for a length of 0.05 feet. In this particular case, this is 0.6 inches. Always convert to inches, don't forget that. And that would give you L over square root of C, gives you 0.6 square root of 2, gives you 0.424 inches. And you find your actual slenderness ratio. This is LE over your radius of gyration, 0.424, 0.144 is equal to 2.93. So what you can see is that your RA is actually less than 10. So the approach, what we recommend that you always do, let's do two parts of the problem. We are recommending that you always just is safe enough just to say this is equal to sigma yield in compression times area. And if you do that, you get 32,250 pounds. Okay. Now, you can also, if you wanted to, you could make the good argument and say, actually, what I can still use my JB Johnson. That should be valid because I am really working this region here. And this region, JB Johnson is valid, right? And then you have your constant sigma yielding compression there, and maybe a small segment here you say is still valid. Let's see how much is it worth the effort. So if I zoom this part here, if I just zoom it, it's going to look something. I'm going to exaggerate that part, okay? So it's going to look something. This is your and this is this. So I'm zooming this segment here, and this is the location. Sorry. And this is the location somewhere here is the location that you're evaluating. Okay, that would be a location right here. Okay, this is your 2.93. I want to show you that sometimes it's not even worth the exercise or the time to do this, to be that rigorous, but you can if you want to. Area is equal to sigma yield in compression minus E sigma yield in compression, RA divided by 2 times pi squared. So that would give you sigma critical is 32,240 pounds. You can see that from both sides, the difference is that much, and it's not worth the effort. And we do this very often. Sometimes you want to be very accurate, but it's really in this particular example, it's not worth because it's just the same. And you have got the same answer way quicker than just applying all this equation. But if you wanted to, you can do that. And just want to point out that this value here is the value that's substituted inside this RA. Okay, so let's go to your third case where you want to find your P critical, and this is L was 2.5 feet, and that is equal to 30 inches. So LE is equal to L over square root of C. That will give you 30 divided by square root of 2. That gives you 21.21. Your actual slenderness ratio is LE divided by radius of gyration. So that gives you 21.21 divided by 1.44, and that gives you 14697. So you can see that your RA is actually bigger than RC. So what this is saying is that if you have your buckling curve, what he's saying is this particular value, the RA that you have, this is your slenderness, critical slenderness ratio. Your RA is somewhere over here. This is your RA. So anything beyond this side, we use the Euler equation. Okay, so therefore, using the another variation of the Euler equation, and I derived this for you in class, in your notes. I would like to use this form. Note that this comes from nothing else than area EILE cube. Okay, there's a pi squared. These two expressions are completely equivalent. Okay, I'm sorry, this area doesn't go there. So these two expressions are completely equivalent. You can use either one of them, but since I already have my actual slenderness ratio, this becomes way more convenient. That gives you 10,280 pounds. So these are the critical slender rate this is the maximum possible load your problem can have. Okay, so now let's go to the second part of the problem. The second part of the problem states the following. This part of the problem says, now let's go with the last case, okay, this case, for which we know that the critical load is actually given by 10,280 pounds. We just found that for this case. So you can see 2.5 feet. This is the actual maximum load. Okay, this is the load, and he's saying what he's saying, and I have an applied load I have a P applied to the problem of 10,000 pounds. And then the P applied in the problem will be nothing else than the design factor times P. In your case, this is 1.1. So this will be 11,000 pounds. Okay? So as we move on in the problem, in this particular problem, we know that you have two things in the problem. How much is allowable? The allowable is going to come from your J.B. Johnson, right, analysis. So it's going to tell you for a certain slenderness ratio, how much is the maximum load you can have. Okay, so this is allowable. That would be nothing else than P critical divided by area. Okay, then you also have P required. What is the requirement of your column? That's going to come from your P applied, which we already found, and know that P required is nothing else than P applied divided by area. Okay, so moving on, we know your factor of safety is equal to allowable divided by required, can also be equal to P critical divided by P applied, and that comes because the fact that you know that in order to find your load, you can just multiply by area, correct? but area and area are the same on both on top and bottom, so they will cancel out. It's the same cross section, so that's why you end up with this. And we also know from our discussion that you got three cases. You got the case when this is bigger than 1, this is safe. You got the case when this is equal to 1, this is onset of failure. It hasn't failed yet, it's just an onset. Okay. It is less than 1, where you definitely your structure has failed. Okay, so let's see what happens in your particular problem. You find your factor of safety, your allowable P critical. Let's use this equation just because I have the loads. This is how much was available in the problem. This is how much I really need in the problem. And you can see them getting a value of 0.934, which is less than 1, and this is not acceptable. So what do we need to do then? It fails, right? The problem says if the design safe is safe or not, if it will withstand. Because it's less than that, it's not going to withstand. What's really happening in this particular problem is the amount of load that's available. Okay, the amount of load that's available is not enough. It's asking for me, can you give me more? I need more. And that's just not possible. I don't have more available. I got a bag of 20 oranges. I cannot give you 21. I don't have them. So your structure will not be able to comply for what your requirement is. So you got a couple of options, right? I can change the load, but changing the load is not an option. The other option is we can change the area, right? I can change the dimensions. So I got really three options. I got three options. The first option is change the material, right? Because your P critical depends on your material. I can use a stronger material. Second option is size. I can change the size. Third option is the load. I can change the load. Okay. In this particular problem, let's assume this is not an option and this is not an option. Okay. We are assuming that. Okay. Assume that these two are not an option. So the only option that left is to change the size. Okay. So to change the size, then let's go back to our equations now. Then what we know is that for this to be safe, this has to be bigger or equal than 1, or sigma allowable has to be bigger or equal than sigma required. So if I replace my values here, this is same as P critical divided by area has to be bigger or equal than P applied divided by area. And you can see that both sides, area cancels out because it's the same area. So this is P critical has to be bigger or equal than P applied. Okay. Now P critical using Euler's equation gives you this equation right here, LE squared has to be bigger or equal than P applied, or further expanding this equation, replacing the value of your moment of inertia, you find this is BH cubed times pi squared E over LE squared. So we're bigger or equal than P applied. Now let's leave the dimensions on this side and move everything on the other side. and you find the following: bh cubed bigger or equal than 12p applied multiplied by LE squared divided by E times pi squared. So if I replace all the values here, I get the following. So this whole expression is equal to 0.201 if you replace all this. I really have two options here, okay, when I want to do this. Or I could do a combination of two also, but let's suppose I want to keep the value of h fixed, okay? So h is going to be fixed at 0.50 inches. That's given in the problem. So if I was to do that, you can show that you can solve for b. So b has to be bigger or equal than 12 p applied LE squared over E pi squared h cubed. If I replace it, you can see that b has to be bigger or equal than 1.5 inches. So this is one option. This is with h equal to 0.5 inches. This could be one possible option. The second option is, now let's fix b. So let's keep b equal to 0.5. Let's not change b, and we solve for h. Okay, so we did that. H is actually then going to equal to 12p applied LE squared pi cube E over B, and take the cubic root of all this, and then you can show that H has to be bigger or equal than I'm sorry, this was 1.5. This is 0.51 inches, and B is equal to 1.5 inches. So this is the second option. So if I was going to choose between these two options, and I want to know now which of these options is actually a reasonable option and I would like to use, then I would recommend, since we are really working with a very thin strip, right? I got two options here. And I'm working with a very, very thin strip, right? It's very long in this direction. Typically, I would like to increase this dimension over making this even longer. But then that could lead to other problems, maybe twisting many times or many other issues. So if there's one possible solution that I strongly recommend that we use in this problem, the recommendation would be, let's go with the higher h, that is 0.51 inches, and let's keep the b fixed. You could also play the combination of changing b and h to find the optimum answer. Okay, so this concludes this example number 2. And note that you can also always run my Matlab code as well to get these answers. Okay, just kind of show you how your Matlab code actually works. Let me find that for you. Just give me a second. The Matlab code is actually under Matlab. Okay, and the function that you will call, the primary function, is called buckling, and you open it. Show you how that works. Okay, so you can see we are working in the Matlab. I usually like to call a new folder with the example I'm working with, so I'm not messing the main code. And so you just press you press this play, so you runs the code. And now that the code is running, just give me a second, you go up here. And now it says what you're working on. You're working on inches? Yes. What are the units? Let's suppose I'm working in KSI. You have to be very careful and consistent if you put PSI or KSI. Now in your problem, it says it's 1.5. That's the buckling load. That's the design factor for the second problem. And then it's asking, pay close attention. It's asking in KSI, okay? But that's what I told you. So in KSI would be 43, and this is 30,000. Okay, you can go to the notes. Has to be, because this was given in 30 times 10 to the 6 psi, so then it becomes 30,000 ksi. Okay, what is the length of the column in inches? So the length of the column in inches in this problem was 30 inches. Okay, is 30 inches. The constant, the end constant was 2. And what do you want to find? Well, what we know is we know the axial load, and we want to find the dimensions. Or given dimensions, find the critical load. Given the load, find the factor safety. Okay, so let's start with the first one. Okay, so let's suppose this is given, right? The number one, the load, given load, find dimensions. And what is the load? The load is 10,000. And you can see that immediately it calculates the applied load to 11,000, changes that for you. So it's asking it's asking for one of the dimensions. So the B is given, this is 1.5. Okay, then gives you a lower bound. Even if you put 0, even if you put a 0, it will change to 0.00001, because 0 it will blow up. So it always starts with a very small number, and then you can put a value of h. Let's suppose let's just use the same value that you gave as a starting point. Let's put 0.8. Then just give me a sec. Okay, so I was able to, I was running the wrong code. So the problem when you're solving is going to give you a couple of things. It's going to give you a printout here in buckling.txt. This file actually has all the answers, the output that you're seeing here. And then it gives you all the iterations. You can see I started with this iteration, and it started with the intermediate column, and then it went along and say it ended up being a long column, and this is the answer, and that's the answer actually we got by hand, right? And then says the column is long and uses the Euler equation. The second question, and also if you look at the problem, it gives you a plot on how this is optimizing. It started a point here and keeps on going until the factor safety is equal to 1. These are the iterations. These are the various iterations that your plot actually goes through. Okay, so now do you want to solve? Do you want to do the problem again? Yes. So let's run the problem again. So 1. Yes, I want to run the code again. What is the column length? Let's run for the case I want to find and fix is 2. So now in this case, given the dimensions, find the critical load. Let's suppose I want to do that. So run the case number 2. So it's a rectangular case, and I have the dimension, the height dimension is 0.5. The width dimension is 1.5. Give me a second. Okay, so when you run this, you're going to realize that you get the load of 10,280 pounds that we were looking for. Let's suppose we want to run this code again for the same case. Okay, so yes, I want to run the code. Give the length 30, and this is 2. Let's find the factor safety given dimensions. Case number 3 is a rectangle, is 2, and the applied load is 10,000. We are using 11,000 as you can see. The dimension was 1.5, the height was 0.5, and you can see that it gives you 0.934 is less than 1, and it says the column will fail due to buckling. And then if you want to run this case again, you can run it again, you can run it again, you can just say, no, I'm not interested. Okay, this is how your Matlab code works. This is the main file that you're running. And all the equations are given according to your textbook as well. Okay, so this officially concludes your example number 1.